Okay, thank you for my coworkers for coming to this talk and other miscellaneous audience members. Yeah, so I'm Dave Kleinschmidt. I work at Beacon Biosignals. I'm going to tell you about some internal tooling we developed called OndaBatches.jl, which, like the title says, is a tool that we use for doing continuous, repeatable, and distributed batching for our machine learning applications. Okay, right. So to start, who am I? I'm a research software engineer at Beacon Biosignals. And the team that I'm on has the mandate to build out internal tooling to support the kind of quantitative and algorithmic development work that we do. And so that's the sort of the ambit under which this work is being done. So who are we at Beacon Biosignals? I just yanked this from a press release because I didn't feel like recreating our elevator pitch. But yeah, Beacon Biosignals has engineered a machine learning platform designed to interrogate large EEG data sets at unprecedented speed and scale. Yeah, great. It's good, right? Yeah. Yeah, so okay, a couple of things to call out here, right? EEG data sets, I'll say a little bit more about what that looks like, how we represent EEG data, the sort of structure and nature of that data. And we have this speed and scale, right? The other things to call out there, right? So we work with kind of data that's not like, you know, large language model size, but it is like inconveniently large, right? So it's not something you could put on even one large machine, right? So we do have a real need for like a genuine distributed tooling. Okay, yeah, so why did we make this? We made it because we had a couple projects where we were basically repeatedly developing the same kind of tooling to basically build batches to train our machine learning models, right? Yeah, and so we're building batches out of like basically what is annotated time series data. And I'll say a little bit more about what that means and why it's a sort of, why there's some work that's required to actually do that, right? Okay. Yeah. So the data that we work with is sort of the input data into these models is like multi-channel, regularly sampled time series data. So something like an EEG recording that's sampled at 128 samples every second, and you have a couple electrodes on the scalp, right, that are all sampling in parallel. And the sort of machine learning tasks we're talking about here are like image segmentation style tasks where the target is basically a dense series of labels. So say every 30 seconds of the data, you need to assign a label to it, right? Next, man, this clicker is not great. Come on, you can do it. Okay. Okay, and so the input data specifically is we have this format that we developed called Onda. The representation of the in-memory representation is a samples, capital S, right? And then the labels they come in natively in the form of something we call an annotation. So an annotation literally is just a time span with some sort of associated label attached to it or whatever other metadata you want, right? And so somehow we have to massage these samples and annotation tables, they're stored in tabular form, into numerical tensors that you can chuck into your favorite machine learning model, right? Come on, forget about that. Okay, okay, so right, a little more preparatory remarks. Who is this talk for? I think there's sort of two potentially interested audiences here, right? So one, maybe you're a machine learning engineer who, like us, is looking to model large time series data sets, and you want to actually use OndaBatches or something very similar to it to build your batches to train your models, right? Two, which I think is the more likely case for this audience, well, I would say that if the majority of the audience was not my coworkers, that maybe you're interested in developing similar tooling like this, and you're interested in how we build these kind of reusable tools in an organization like Beacon, right? It's a startup, pretty small, but we still have a need for these sort of like reusable tooling that's like well documented and tested and versioned and stuff across our organization. Okay, so yeah, why might you care? Well, first of all, we actually do use this tool at Beacon. This is not like a proof of concept or a toy. This is something that we use in production for training and evaluating our models, right? And I think in the second case, right, this is a potentially useful example or maybe a cautionary tale for how to like wrangle inconveniently large data that has this similar kind of structure, and also some of the sort of the pitfalls or the nuances of doing this in a distributed setting. So how do you take something that might work locally, synchronously on a single core, and hoist it up into the cloud to make use of this great scalability of cloud resources, right? Okay, so there's going to be sort of two parts to this talk. The first part is going to be talking about the like overall design, so the constraints we were working with, the design philosophy that guided the sort of the overall structure of this package, and the basic functionality. There's going to be a little bit of an interactive demo. And the second part is going to be how do you, like I said, hoist this sort of system into the cloud to make it work in a distributed setting, either in the cloud or like on a large machine where you want to do multiprocessing. Right? Okay, so our goals when we set down this road to make this package, right, we wanted to make a batching system that was distributed because our machine learning pipelines are distributed due to the nature and the scale of our data. We wanted to make it scalable so that we could handle data sets that are out of core, and then we can like throw more compute at any kind of like batch pre-processing or featureization that we need to do, so that like the goal is basically to like computers are cheap. We should never be wasting engineering time to like work around the fact that our pre-processing and our batch loading is a potential bottleneck for the machine learning training, right? We wanted to make it deterministic and reproducible, right? So that you always guarantee to get the same series of batches, so we can actually repeat experiments in a meaningful way, right? Which turns out to be surprisingly challenging if you're doing this in a distributed like asynchronous setting, right? We also wanted to make it resumable for the same reason. So if you checkpoint your training at a single point, but you have some state associated with the batching process, you should be able to restart the stream of batches from that exact state. So you could restart training from a checkpoint if you wanted to. Or if you needed to debug something, you go back to a checkpoint and restart the batcher so you can like access the batches that the model actually saw when it failed or the validation loss went crazy or something like that, right? And we wanted to make it, because this is an internal tool that's meant to be used broadly across different projects, we wanted to make it sort of flexible and extensible via normal Julia mechanisms. So that what that usually means is multiple dispatch. Right? So we wanted to build in hooks so that our engineers who are actually using this tool internally to build the machine learning algorithms can like design their own batching systems and design their own weird featureization schemes and do whatever their wild hearts can imagine. Okay, good. So the philosophy behind it was that, so this is, I think, the sort of most important point, and this has become a kind of a, thing I say all the time. So the other main Julia thing I've done in my history of Julia is build statsmodels.jl, which has a very similar philosophy of separating the planning and execution stage. But what we want to do is separate out the cheap parts of batch building where order matters, right? So specifying what your batch is going to contain, from the expensive parts that you can do asynchronously, so the materialization, so pulling the data down off S3, doing some kind of featureization to it with all the data in memory, right? That's the first design philosophy. The second is that we want to build on top of existing tooling at Beacon specifically, because this was originally developed for internal Beacon stuff, but all the tooling we're building on is open source and anybody can use it. So what that means is we're using this package called Legolas.jl, which is basically for designing, for making like schemas that are associated with record types that you can put into arrow tables, because we store almost all of our tabular data in arrow format, right? And then those schemas are specifically going to be built on top of like OndaBatches.jl schemas, which define the sort of format, metadata format, and coding information for our signals and the annotation schema. Okay, we want to use sort of base iterator flavored patterns to generate the sequence of batches. And the reason is that we want to sort of force our users to handle the state of the batcher. We don't ever want the batcher to be something just happening. We want the user to actually have to explicitly say, hey, I want to get a batch from this state, right? And we also want it to be flexible enough so that it can be readily useful across different ML efforts at Beacon and potentially beyond. Okay, last thing is we want to use this is a sort of more kind of high level like package design philosophy, but because Julia has this mechanism of multiple dispatch, we want to use function calls that we control, that are defined, that we own in the OndaBatches, to provide hooks where users can then go in and provide their own types so they get called with those functions, right? And the methods for operating on them to customize things like featureization and channel selection and yada, yada, yada. Okay, so great. That's all the sort of like background and design philosophy. Let's talk about how it actually works, right? So I have a little code snippet here, which is basically just a mnemonic to remind me to go and launch a live demo. So I'm going to do that. Okay, so we're going to start by loading some signals, a signals table and a labels table, and we're going to look at those a little bit. So the signals table is just a data frame, right? You can see it has a bunch of fields. We can use describe to have a look at it, right? So this is basically the schema, the Onda signal schema, right? So you see a bunch of stuff about like encoding, right? So how we were going to quantize this into an integer representation that we store on disk. And yeah, that's the first bit, okay? So we can use Onda.load to load one of these. So the signal row basically refers to a like LPCM serialized or whatever serialization format you want to use. It's serialized somewhere. It could be on disk, it could be on S3, it could be wherever you want. So you load it like this, and it then materializes the samples into memory, right? So you can see that this is our multi-channel time series. So the time is on the like columns are time and rows are channels, and you can see the channel labels up here, right? Channel names. That's sort of the main thing to focus on. And then there's also a sampling rate associated with this, right? Okay. So that's that. Those are our samples. So this is what the data looks like coming in. So now let's look at the labels, right? So the labels table looks like this. So it has the things to pay attention to here is that there's a span. So this is a time span, which has like this will be 30 seconds long. I'm not going to print the whole thing for you, right? And then it has like a stage label associated with this sleep stage, right? So whether you're awake or NREM sleep or whatever, right? Okay, so the first operation we do in OndaBatch is we generate something called a labeled signals table with this label signals function. So you'll see this table looks a lot like the signals table, and that's not an accident. It basically is. It's just a signals table with some extra label information glommed onto it, right? So you see it has these extra columns now called labels and label span. And so labels, if you look carefully, is itself a samples object, right? So we've taken these annotations, which are basically just time spans, like slices of the time, and we've converted them into some regularly sampled label thing that we can then use to glom together into a tensor as a objective target for our actual machine learning optimization problem, right? And then there's a time span, which is the span of the signal that these labels are associated with, because the labels don't always start at the very beginning of the recording. They might start at some godforsaken thing. We have like some data sets where they're like some weird off by one error, and they start at like 101.995 seconds or something. So there's like a 5 millisecond offset or something. So okay. Yeah, so this is what the actual labels look like. One example of what the labels look like, right? So you see now this is also, again, samples. This one just has one channel, and they're sort of like indicator coded. So we've encoded our stages into like UN8s, right? So like wake is 0 or a 1, and REM 1 is a 2 or something. Yeah. Okay, cool. So that's the sort of like, so that's the first level of transformation, right? We turn the annotation time spans into this sort of like time series of labels, and we attach them to the signals table. So now everything is in a nice, neat table that we can use to build our batches. And then the package itself defines one batching scheme, what we call random batches, right? And so you can provide like weights associated with the different signals, weights associated with the different label classes, right? So if you want to over or undersample some of the things, right? You can specify the number of channels that you want to sample from each signal, right? In a batch for each batch item. So we're going to be randomly sampling two channels per batch item. And then you specify the batch size, right? So how many batch items go into an individual batch. We're just doing 3 here, a toy example. And you specify the batch duration. So what this is going to do is it's going to sample from 3 different randomly chosen signals. It's going to sample 5 minutes of a random 5 minutes out of that signal and the associated labels. And it's going to glom those together into tensors that we can put into our models. Okay, right, so the next step is to define the starting state where you're going to start sampling. So for this batch iterator, the state is just a random number generator that's going to be threaded through all of the randomization calls, right? Then we call this function iterate batch, right, which is like base iterate, but it has an underscore batch because we didn't actually want to define methods for base iterate. And that returns one batch and the updated state. Okay. And if you look at the batch itself, the batch basically has the same, very similar schema to the labeled signals table, right? With one extra column here called batch channels, right? And so like you can see for the first item in this batch, we randomly selected the CZ and C4 channels to include in the batch. Okay, now, so that's the batch specification thing, and that's all it is doing very cheap, quick little operations on the labeled signals table. Then we can call this function materialize batch, which takes the batch, which is just a little table itself, and creates our x and y tensors. And so the x here is like this, right? So you see now it's a, let's see, 2 by 38,400 by 3 array. So that's like 5 minutes of data sampled at 128 hertz. And it's two channels per recording, and 3 recordings that were randomly sampled. It might sample the same recording twice, by the way. But if you don't want to do that, you can define your own iterator to do whatever kind of fricked up sampling scheme you want to use, right? Okay. And the labels, the y, are also a tensor, right? So they're a, let's see, 1 by 10 by 3. So these are 30-second labels. So in 5 minutes we get 10 of them, right? And the great benefit to our users at Beacon in this package is that there's all kinds of like fiddly crap that you have to do behind the scenes to make sure that these labels are actually aligned with these samples in the data, right? Because the sampling rates can be different, they might not align perfectly and all this stuff, right? So like one of the big benefits of having a package that does this, even so leaving aside all the distributed stuff, is that like we now have a surface that we can test and document and maintain that like removes a lot of potential mistakes that are very easy for our users to make. Right? So like one of the reasons to build this tool in the first place is to do that. Okay. Okay. There's additional functionality for like persisting. You can persist the labels onto disk or onto S3 if you don't want to. If your label set cannot itself fit in memory in whatever machine you're using to do the training, right? But we're not gonna touch that. So just for time. Okay. Let's go back to Chrome. Oh yeah. Okay. So I think the next thing here is basically another little demo. Why does this? Okay. I think I have to do this. Okay, yeah, so I want to talk a little bit now this like extensibility functionality here, right? So let's imagine a model that requires a specific set of channels as input every time, right? So in that batch sampling thing, we were just grabbing 2 random channels so we didn't care, right? That model, that's an appropriate scheme if your model just needs like some channels, you don't care what they are, right? But imagine a model where like you need a very specific montage, a very specific set of electrodes on the head, right? But maybe you're in a world where like your data set isn't super clean or normalized or harmonized and doesn't always have all of those channels in every recording, right? So in the bad old world, right, our algorithm developer would write their own batch loading thing. We're like, oh, give me all of these channels. And like, it works fine until you hit a recording suddenly that doesn't have a channel and your whole thing crashes and falls over and you have to restart again, right? After like spending an hour waiting for all your cluster to start up and everything to precompile and yada, 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 right? So if you wanted to, you could build in some guardrails around that. You could build a little struct we're going to call 0 missing channels, where you give it a list of channels that have to be present in the input in a particular order. And then we have this hook called get channel data that is run in the materialize batch step. Right? So this is an opportunity to, once you've loaded the samples for the time span that you're trying to access, right? You can pull them down, you have them in memory, you're materializing the batch. You can then like access the channel data from that samples object in whatever way you want, right? As long as it returns a tensor, like OndaBatches will be happy, right? So in this case, it basically just goes to the channels that you have to have, and for all the ones that it finds that are present in the samples, it'll stick them in the output, and otherwise it'll just fill it with zeros, right? Yeah, so let's see a quick example of this, right? So I'm just gonna define this struct here. Let's create one. So I created one here that has like a bunch of real channels and then like a thing that's not a real channel. So that's not present in any of our demo recordings here, right? So if we call get channel data on the samples we loaded earlier, right? All 4 of the samples except for the not a real channels except for the not a real channel are present, right? But then you see the bottom, the 5th one is actually filled in. Okay. And so normally the way you would use this is that like you would define your batch iterator to like plug this in the batch channels field, right? So when it's iterating batches, it would plug it into the batch channels field. But instead we're just going to manually splice it into the batch we generated earlier, and then just to show you that when you call materialize batch on this, it actually does what you want. Yeah, let's see, right? Yeah, so see in this batch, like some of the, so the first and the third batch item don't have all those channels present, right? In fact, they only have one of the listed ones is present. And so you can see they're all zeros except for this one row here. Yeah. So this is a way that our users can, in their own package without modifying the OndaBatches code, hook into the way that we're actually materializing the batch and like do whatever they kind of customization they want, right? Okay, let's go back to Chrome here. Okay. Okay, so now I'm going to switch over in the last like however many minutes I have, classic running out of time, and talk about like our distributed batch loading, right? And so I want to say a little bit about why we wanted to do it, right? Which is that like, you know, different models have different requirements of the size of the batch and the structure and how much pre-processing would have to be done. So in a package like OndaBatches, which is meant to be a reusable tool across efforts, we don't want to be super opinionated about how much resources we assume our users are gonna need, right? So again, we want to provide a sort of a flexible system that's of like just flexible enough to use for users to actually do the things they need to do, but not so flexible that they can shoot themselves in the foot with it all the time, right? Yeah. Okay, I think I said more about this, right? So let's talk about like how we actually go from something where we were fundamentally just like calling local functions in a REPL, which is what I was doing here, to like executing this on like 100 Kubernetes pods, right, or 10 more realistically, but right. Okay, so the first thing is that instead of having a function that like is going to return the batches, you want to stick them into a remote channel, and the remote channel is like one of the sort of like multi-processing communication like primitives that Julia provides, right? It's basically a way that you can sort of like feed values in at one point from one process and have them like access them on another. Right? And so here, like the kernel here is very similar to what I was the demo just running before, right? So you iterate a batch from a state, we're going to materialize it, and then we're just going to like put onto the channel this the combination of the materialized batch and then the state, right? Because again, we want to make sure that like users are forced to handle the state. We really want to, like, this is like one of the opinionated things about this, like we want to make it so that like, yeah, you have to handle the state. Yeah. Okay. And we wrap this all in a function, and we can remote call that function, right? So we remote call start batching with like whatever worker process we're going to use, and then we provide the arguments like this. And this returns a future, right? So like all of our remote call in Julia returns a future, which is something that will have the value whenever the function returns, but who knows when that would be, right? Whenever it executes and then returns. Okay. Next, okay. Okay, so that's how you're sort of hoisting the actual batch loading process into another process, right? But we have this issue now where like we want to load probably more than one batch in at a time, right? That's the sort of one of the bottlenecks we want to remove, right? And that gets a little bit trickier because now we want to make sure we're actually maintaining a fixed, predictable batch order. That was one of our design constraints, while at the same time like parallelizing the loading of the batches, right? And the way that, so this is actually not how we do it anymore, but this is sort of the initial implementation, which we cycle through the workers that are available to us, right? And then like we're gonna remote call, we're gonna iterate the batch locally on the manager process because that's cheap and fast. It doesn't take up a lot of space. And then we're gonna remote call the materialize batch function with that batch on one of our workers. And that again, remote call generates a future, right? So now we have like a bunch of futures that we generated, right, as part of this loop, and then we just go through the futures one by one, wait on each future when it's ready, when the worker is finished materializing the batch, then we throw it on the export channel. So now we sort of like have another layer of like distributed indirection here, right? This is getting complicated fast, right? This is like kind of annoying. Okay, and then that's now our kernel that we run in this infinite loop, right? Instead of just the sort of serial batch loading. Okay, great. Easy, right? So no, it's not easy, and it's pretty subtle and pretty finicky. I'm not even going to get into like how tricky it is to like make sure that errors get surfaced properly to the user, right? So that like our users, when they're running their algorithm, they're going to make mistakes and bugs are going to happen, right? And so we want to make sure that we get an informative stack trace. We don't get like a bad state, like a deadlock or something, right? Where it just stops working and you don't know why, right? And there's also a lot of like kind of annoying bookkeeping that has to happen. So you have to keep track of the future that's returned by remote call at that like start batching level, right? So just like to see if the process has failed or not. You need to hold on to the remote channel so that you can pass it off to like the actual training loop that's like consuming the batches and running them through the GPU and doing backpropagation. And you have to like hold on to the batch iterator itself, right? And not to mention the state, but the state we're forcing the user to handle again. Okay. Yeah, and so like one of the other things that this package does is provides a sort of encapsulation, we call a struct called a batcher, which does the bookkeeping for you and like does like a lot of work and a lot of testing and a lot of a really painful code review, which my colleague Eric has really been instrumental helping with, to make sure that like errors that can happen at any one of these stages are actually appropriately surfaced, don't lead to deadlock, and yeah, and so I think like this is another sort of like a high-level package design philosophy, right? Which is that, again, when you're developing a tool, you're looking for an abstraction that is going to provide just the right amount of flexibility and surface just the right complexity to your users that want the sort of irreducible, unavoidable complexity, right? But not so much complexity that it's annoying to use and that they're going to be tempted to kind of go off and do their own thing, right? Yeah, and that's good for your users, and it's also good for the developers and maintainers, right? So it makes it even in principle possible to test all the possible error cases that could happen in this kind of system, right? If you have a restricted API where you have this like batcher thing. Okay. Yeah, thanks. That's all.
Okay, awesome talk. Sorry you had to be the last person to talk at JuliaCon. But if anyone has any questions, I'd be happy to hand it off. Sure.
Hi, thank you for the talk. So I think somewhere in between you mentioned that the labels may not align with the time samples. Could you talk about that more, why that would occur?
Oh yeah, I mean it can happen just because like, you know, I don't know. This is more kind of question about the nature of the data that we're dealing with, right? So a lot of times these are things that, so for this case, it's not all that common because like, this gets a little more into the nitty gritty of like the specific type of data. Like sleep staging is typically done starting on like even 30 seconds or like whole seconds at least, right? So if you have like a integer sampling rate, that's also gonna happen. But there's a lot of software that people use to annotate other kinds of events that can occur during an EEG, where they just sort of like click anywhere, right? And then like the software exports it to some other format and we import it to our format. And somewhere in that meat grinder, you can very easily get into a situation where like, if the signal is sampled at 128 hertz, you might get something that starts at a kind of weird random millisecond, right? That doesn't actually, like an annotated event that starts at a weird random millisecond that doesn't actually line up with that. So yeah, that's sort of why you get to those situations. Yeah.
Any other questions? Yeah.
Thanks, Dave. Great talk. My question is, how do you know where to draw the line in the functionality you express to users and what to hide from them? And then also, how do you prevent sort of complexity creep over time as it kind of grows into its niche, its use case?
Yeah, and I'll answer the second one first, which is that I think actually this, like, I'm starting to have, I'm filled with regret about this whole batcher service thing, because it has become enormously complex and difficult to maintain. Even when I have to go in and like make a change, it's really, really hard, right? So I think the thing is like, you just sort of like, you take a guess and you give it a try, and like eventually you have to be prepared to just sort of like cut pieces off when they become too complex or difficult to maintain, right? Or like, yeah. And as to the first part of the question, like, you know it when you see it, I guess is the only thing I can say, right? I think it's really, it's one of these, it's a real judgment call. And I think it requires like, like, I always like to say that like most of software engineering is like actually like sort of human and social problems and not technical problems, right? Because it's like, you're trying to like do stuff with computers, with other people, right? The computer is the easy part, frankly, right? The other people are the hard part, right? And so it's like, I think it is a lot of like, you need to be empathetic towards your users and sort of understand what they're doing and like have a lot of like theory of mind for like where they are going to run into trouble and make mistakes. And a lot of that stuff you just learn over time, right? And like I think like one of the sort of like the life cycle of this package started off in a very much more constrained case on one machine learning effort. And then eventually it grew into sort of, we try to generalize it and use it more broadly. And as we were doing that, that's the sort of point where you start to yeah, you start to think about where can we generalize this and where can't we? But it's like, yeah, I think it's something, unfortunately, you have to learn over time. So yeah.
I'm sorry, I'm going to have to cut us off. We do have a closing speaker or something going on. I don't know.
Something's happening.
Yeah, I think it starts now. Yeah,
Yeah.
so we got to go. Sorry.
Thank you.
Thank you again.